This tutorial will show two different ways to utilize the nonlinear gap element in SAP 2000. First, we will show how to perform a building pounding study. Here, we have a 7-story building adjacent to a 4-story building. Although the column lines are separated by a 16-inch space, we are going to assume that the physical gap between the buildings is only a 1/4 inch. We will subject the buildings to an earthquake ground motion and use the nonlinear link elements to model the gap. In this example, we will use fast nonlinear analysis, or FNA. We start by defining the gap element, which is done under the Define Section Properties Link Support Properties command. Here we will add a new property of type gap, which we will name gap. It will have properties in only the local U1 direction, which is along its axis. It will be a nonlinear element, and if we click on the Modify button, we can specify its nonlinear stiffness and the opening. We want the gap element to be stiffer than surrounding objects, but we do not want too large a value, as that can cause numerical instabilities. We will set the open value to 0.25 inches, our starting gap. Next, we will window in between the two buildings so that it will be easier to draw the gap elements. We go to the Draw Two Joint Link command and make sure that the property of gap is selected. We will draw the gap elements across the opening between the buildings at each floor level. We will click on the Select button to leave the drawing mode. Next, we will define the time history input. We will use a function from a file in this case an El Centro earthquake. This particular file is in a time and function value form with 3 data pairs per line. Now we will define our load cases. We have 2 default load cases, dead and a modal case, which we will now modify. We will change the mode type to Ritz vectors, and we will ask for a total of 30 modes. We need at least 15 for the 7-story building, the 4-story building, and the 4 links, but we'll ask for 30 to be safe. For Ritz modes, we need to define the starting load vectors. In this case, we will use acceleration in the x direction and the built-in deformation load for the links. We will also add a load case for the nonlinear time history, which we will call pounding. For this example, we will use the fast nonlinear analysis, which is a nonlinear modal time history. It uses the Ritz vectors. The loading will be the El Centro acceleration record, scaled from G units to inch units. We will use 5,000 time steps at a step of 0.002 seconds for a total of 10 seconds. We will leave the modal damping constant at 5%. No other changes will be made. Before we run the analysis, we will change the display so that we may see the model behavior slightly better. We will turn on the Extrude View option and will remove the links from the display. We will now start the analysis. First, we will display the deformed shape for the pounding load case at a time of 6 seconds. We can clearly see how the buildings have separated. Next, we are going to create a plot of the input ground acceleration. We will save it as a named set called Ground Excel. The best way to see the pounding behavior is to create a video of the time history response. We will create the video using the pounding load case for a time span of 10 seconds. We will also ask that the previously defined ground acceleration graph be displayed. We will change the magnification factor to 50 so that the deformations appear larger and easier to see. Let's see this once more. This concludes this first example. For the next example, we will illustrate how to use the nonlinear gap elements to model uplift in columns. We will use the same 4-story, 1-bay building from the first example, subjected to the same earthquake ground motion. We will use the nonlinear link elements to model uplift in the vertical direction. However, rather than using Ritz modes with the fast nonlinear analysis time history option, we will use a static nonlinear analysis to apply the gravity loads, followed by a direct integration nonlinear time history analysis for the earthquake. Again, we start by defining the nonlinear link elements. We will modify the previously defined gap element. We will modify the U1 nonlinear properties by changing the stiffness to 30,000 due to the larger axial stiffness of the columns. And we'll switch the open variable to 0, as the gap should start in the closed position. Next, we will draw the links using a one-joint link. Again, make sure that the gap property is selected. When drawing one-joint links, the U1 direction is assumed to be vertical. Next, we will verify that our ground motion is still the El Centro acceleration defined in the first example. Next, we will set up two new load cases. The first will be a gravity case, where the dead loads will be applied in a static, nonlinear fashion. This is done so that we can apply the dead loads sequentially prior to the uplift analysis. The second case we will define will be for the time history analysis, which we will call uplift. This is a nonlinear case using direct integration. It will start with the initial conditions determined from the gravity case. It will again use the El Centro acceleration record scaled from G to inch units. Again, we will use 5,000 steps at a 0.002 time step for a total of 10 seconds. The proportional damping will be specified by period. We previously calculated the first period to be 0.98 seconds and the second period to be 0.28. We will use 5% damping in both modes. Note that the program automatically calculates the mass and stiffness proportional damping coefficients. For the time integration technique, we will use the default Hilbert-Hughes-Taylor method, which is typically the preferred method. Note that when alpha is set to 0, the method defaults to be the same as the Newark method. Alpha can range from 0 to -1/3, and we will leave it as 0. The last thing we need to do before running the analysis is to restrain the base of the columns in the X and Y directions. Remember that translation 3 is in the vertical direction, which is where we have placed the gap elements. Now we are ready to run the analysis. We will shut off the dead load case as that has been replaced by the gravity case in our analysis, and the modal case is no longer needed. Note that the direct integration analysis takes significantly longer than the fast nonlinear analysis in the first example. Upon completion of the analysis, we will display the axial forces for this gravity case to make sure that the distribution looks appropriate, which it does. Next, we will display the deformed shape for the uplift case at a time of 1 second. As previously stated, creating a movie of the time history response is a quick way to review your model's behavior, a valuable first step to ensure that the response appears appropriate. Note the uplift. In summary, nonlinear gap link elements may be used in either a fast nonlinear analysis or a direct integration time history, and should typically have a nonlinear stiffness a magnitude or 2 stiffer than the surrounding elements. This concludes this tutorial on gap elements.